Hey guys, I'm going to go through the process of these various different problems. I'm not sure exactly how far we'll get on this first screencast, but I'm going to go through them relatively quickly, so hopefully you can stay with me, but especially these first couple aren't all that difficult. So we have to find the force of gravity for this first one. Fg is simply the weight. So the weight is, for a 200 Newton gorilla, well, it's just 200. Fg, which is the weight, is mass times acceleration due to gravity. So if you're given the mass, which kilograms and kilograms are masses, not weights, then we have to change those by multiplying by 9.8. Well, 10 by 9.8, so the weight of the cat is simply 98. I don't have to do that in my head, and has units of newtons. And 30 times 9.8 is 294. So that's relatively simple. So force of gravity of the gorilla, 200 newtons, 98 newtons for the cat, 294 newtons for the dog. Close that out. Moving right on to number 2. How much force will it take to accelerate a 600 Newton gorilla wearing special roller skates, blah, 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 across the ground from rest to 16 meters per second in 4 seconds? This is a little throwback to our old kinematic equations, which says Vf minus Vi over t is our acceleration. Our Vf is our 16 at rest. Vi is 0 over our time 4 gives us an acceleration of 4 meters per second squared. We know our mass because we know our weight. Our mass is Fg over 9.8. 600 over 9.8 is 61.22 kilograms. There's only one force. Doesn't say anything about friction. Told to assume there is none. So all you have to do, the applied force will be the same as the net force because our gorilla will only have one force when applied. Total right minus total left. There is no left force. So our net force by Newton's second law, mass times acceleration, 61.22 times 4, which equals 244.9. 244.88 newtons. Okay. Hopefully that's good. For number 3, we have the same acceleration, 4 meters per second squared, with the same gorilla, so our net force is not going to change. We have the same mass, the same acceleration, so I don't have to go through those steps again. Still 244.88 meters per second, newtons. But this time there is friction, so we have to figure out how that plays into the factor. We still know that our gorilla, through our applied force, has a net force of 244.8 to the right, but now we have to take into account friction. And in this case, ultimately it'll be FFK we have to deal with. First part of the question says, though, how much does it take to simply get it moving? Well, to get it moving, we have to beat the static friction force. And the static friction force is going to be 0.6 times the normal force, which is 600, which is 360 newtons. So for part A, it's not really labeled part A, my applied force, F applied, has to be greater than 360 newtons. But to keep it accelerating at 4 meters per second squared, we have our net force, 244.88 newtons. That equals our applied force, what we're solving for, minus our force of kinetic friction. Set that up separately over here. Our force of kinetic friction is 0.3 times 600, which I can do in my head as 180. So subtract 180 newtons, solve for F applied. You're going to end up saying the applied force is 244.88 plus 180, 424.88. So you still have a net applied force to the right, but because you have to overcome friction, you have to push a little harder than just the 244 that you did for problem 2. Alright, now we have a slightly different situation. That same gorilla but this time we're trying to lift the gorilla upwards. So we're applying an upwards force. That's the only force that is lifting the gorilla up. It's just like you're holding a piece of coffee cup or whatever. It's an applied force. It's not the normal force you deal with. The weight of the gorilla is 600 newtons still. So you need to figure out what this applied force is. Well, this is one where we haven't done a whole lot of up minus downs, but we're totally capable of doing up minus down. So that's supposed to be squared, sorry, 2 meters per second squared. Our acceleration is 2 meters per second squared, and that's upwards. Our mass was, again, 61.22 kilograms. So our net force has to be 122.44 newtons upwards, and 122.44 newtons upwards has to be equal to our applied force. You do up minus down, minus 600. The minus means you have to add 600 to both sides, so you're going to get 722.44 newtons. Keep it upward if you want, is the applied force that's necessary. Sorry about that. 722.44 is the applied force necessary to lift the gorilla upwards. Alright, moving right along, going nice and quick. You are pushing on a 400 Newton desk, currently at rest. Anytime you see those words, at rest, key things to look at. Boom, at rest. If you push horizontally with a 200 Newton force, how much friction will there be? Currently at rest, I have to see whether or not I'm pushing hard enough to overcome static friction. So my FFS maximum is the mu s times the normal force. My mu s is 0.7, my normal force is 400 because there's no other vertical. 0.7 times 400 is 280 newtons. So I haven't pushed hard enough. My applied force is less than, or sorry, my applied force is greater. Skip that. My applied force is less than the static friction force maximum, which means that there is still no movement when this is the case. My static friction force, just all over the place. Sorry. My static friction force, going back, my FFS max was equal to 280 newtons. So my applied force is again less than my static friction force max, which means, going back a couple steps, no movement. No movement means my forces are balanced, which means F net equals 0, which means that my applied force minus my force of static friction, FFS, has to equal 0. My applied force is 200, which means that my static friction force, you can see easily, also has to be 200. So FFS equals 200 newtons. Be careful. This is a very tricky problem. A lot of students get caught up on this and would easily have just have stopped here and said, oh, 280. If that were the case, though, you would have had an unbalanced 280 newton force that way, 200 newton applied force, or vice versa. It doesn't really matter. That would have been unbalanced. So this one has to be 200 as well. All right. How much will a 400 newton air conditioner weigh on the planet Mercury? 400 newtons. That is our weight on Earth. It's 400 newtons. To find our mass, which is a property, you take the 400 divided by the g on Earth, which is 9.8. 400 over 9.8, 40.82. 40.82 kilograms. This is a property. This doesn't change, so I can bring that to Mercury. And the weight on Mercury will be the mass times the g of Mercury, which is 40.82 times the 3.6 that we're given, 146.93. Simple enough. Moving right along. Find the acceleration of a 100-kilogram bobsled as it slides down the track. If the track is inclined, blah, blah, blah. All right, so we know it's accelerating because that's what we're trying to find. We don't care about the static friction coefficient. We only care about mu k. On a ramp, we have to break our FG, which is 100 times 9.8, 980, into its pieces, FGY, FGX. FGX is the piece that pulls us down the ramp. FGY is the piece that pulls us into the ramp. And on a ramp, the FGY always equals the normal force. Do this one first. It's going to be our 980 times, if you look at your equation sheet, FGY is cosine of our angle, which is 20 degrees. 980 cosine is 920.90 is what I'll round to. 920.90 newtons. Similarly, FGX is going to be 980 sine of 20, which is 335.18. Alright. I know I'm in kinetic friction, so I have to determine what my kinetic friction force is, FFK. And my FFK is equal to our mu k times the normal force. And the mu k times the normal force, our mu k is 0.1, our normal force is now 920.90, which gives me 92.09 newtons. So, my acceleration, I can find from mass times acceleration as my FFK minus the FGX is what's pulling me down the ramp. So this is my FGX of calculated value 335. So my mass is 100. My acceleration is the unknown. My FFK is the 92.09. I keep that positive because it's up the ramp. This is the down the ramp, why it's negative. We subtract it of the 335.18. That gives us that 100A equals 92.09 minus 335.18. Negative 243.09, which I can do, and you should be able to do that simple math real quick. A equals negative 2.43 meters per second squared. And I know on the answer sheet it says positive, but that's because on the answer sheet it cancels out the DTR. You don't need both of these. You should have either the negative or the DTR down the ramp. I think I'll stop there for this screencast, questions 1 through 7, and pick up with 8 on the next one.